Hi everyone, here we will solve the recurrence relations using the master theorem. The master theorem is used to solve the recurrence relation whenever which is applying on the divide and conquer algorithms. Let's take a and b are two constants and f of n is the function. Then we can define the time complexity of given problem with respect to the input size is n, which is defined on non-negative integers as t of n equal to a times of t of n by b plus f of n. Here a and b always it will be a greater than or equal to 1, that is the positive integers. Here n is the problem size and which is the current problem, and a is the number of sub problems in the recursion. Here you look at that we are taking the bigger problem, that is a n number of n number of n size input is the n, and this n is divided into sub problem n by 2 and n by 2, then n by 2 is dividing by n by 4, here n by 4, it will keep on go until reaching the initial condition in the recursive calls. So here the a is a number of sub problems which we are going to partitioning the single problem, original problem. F of n is here the cost of the work that has to be done outside the recursive calls, and here which is applying the divide and conquer method. Here the n by b, this term is each sub problem, right? So based upon this we will interpret the n by b as a floor value. Then t of n can be bounded asymptotically as t of n equal to a times of t of n by b plus f of n. So here when we are taking the recursive tree n by 2, here also n by 2, here the n by 2 will be partitioned into n by 4, then it will keep on go until initial condition t of 0. So here based upon that the runtime of each of these initial nodes is the runtime of n by b, t of n by b. So the recursive tree contains the depth equal to log b power a. So this depth will be log b power a, and the depth I contains a power I nodes as a leaf nodes, a power I nodes as a leaf nodes. Okay, so this a power I number of nodes is called the problem. So each node is called here problem. So we can define a power log into b power n times of leaf nodes. So here we can substitute the a equal to n times of problems, number of problems, okay, sub problems, right? So now the runtime can be defined as big theta of n power log b power a, this one. So that is the number of sub problems. So here we will have the finally n number of this many number of leaf nodes, this many number of leaf nodes. Okay, so now based upon that we can define three rules in the master theorem. If f of n equal to big O of n power log b power a minus e. So a is here number of sub problems, right? Then here for some epsilon value greater than 0 we can define t of n equal to, this is the this is with respect to big theta of n power log b power a. When you're this is the rule number 1. So here we can write by finding the a value and b value and substituting the d. So this is the degree of given order in the, suppose if you are having n square plus n, so here we will take the degree of this term, so d. Then we can use this rule t of n, the time complexity belongs to big theta of n power log ba, right? If n f of n equal to tighter bound big theta of n power log b a, so here there is this constant is not available, so this is the average case. So then t of n equal to big theta of n power log b power a multiply log n. So here this can be used when if a equal to b power d, right? If both are equal, then we can say the time complexity is big theta of n power d log n. This term can be represented as a d, okay, log b power a. Then here f of n equal to the lower bound n power log b power a plus some constant. When some constant greater than 0, then this can be written as a into f of n by b less than or equal to the c into f of n, right? So this is the lower bound, actually lower bound equation. Then for all n sufficiently large, n value is sufficiently large, we can say t of n equal to big theta of f of n. So f of n is here, we can say a less than b power d. This is the condition, this is the equal, this is the greater than. Now t of n can be big theta of n power d. So d is already we have said log, okay, log b power a, okay. So these are the three rules to define the time complexity of given recurrence relation equation by using asymptotic notations. Thanks for watching.